Hello, everybody. Welcome to this week's iteration of the RI seminar. Our speaker today is Brittany Duncan from the University of Nebraska, the Nimbus Lab. Some of you probably don't know about some of the work they do there, but having seen some talks from this group, it's cool. And rather than consume a lot of time, I'm just going to tell you, enjoy the talk and take it away.
Great. Well, thank you very much for the welcome. So I'll show you, I'm actually going to almost start with a couple of videos just here in a few minutes to set the stage for some of the things we do, because it's actually highly relevant and informs the things that I think are interesting. I'm Dr. Brittany Duncan. I'm an assistant professor and I co-direct the Nimbus Lab. Today we'll talk about drones in public, distancing and communication with all users. But at the beginning, we'll talk about some other things that I just find interesting before we get into the meat of that. So do this every time when I teach class too. Forget to take the control back to PowerPoint. Okay. So my overarching research vision is to improve human-robot interaction for real users in real-world interactions. So this includes both specially trained users in complex use cases, which we'll talk about here in a second, but also just members of the general public interacting with robots in everyday interactions. So I'm going to describe research on how to adapt to and interact with people on opposite ends of the training spectrum in order to understand how to deploy systems in difficult, chaotic environments to improve responses in environmental monitoring and disaster relief domains. And so this is where my affiliation with the Nimbus Lab becomes more important because we focus on, as a lab, which is directed by 4 faculty members here at University of Nebraska, close interaction with the world and the practitioners who would deploy these systems. We primarily focus on unmanned aerial vehicles or drones. I'll use those terms pretty interchangeably throughout the talk. But when I say that, I mean these smaller hand-launched systems that can do different things. And so some of the projects we've worked on are UASRX, which is unmanned aerial systems for prescribed burns, down there at the bottom left. Water sampling systems, so it can go and collect water samples from lots of little lakes or streams that are located close to each other. And then we have some digging systems and some swarm deployment systems that we probably won't get to the swarm deployment stuff today, but it's kind of interesting as well. So the reason I think these problems are interesting is because I want to know how real people will use the robots and how we can improve that for the future. So it doesn't matter what kind of great systems we create in Nimbus. If nobody can use them, then they never leave the lab and they have less impact on the world. That's not been true for our prescribed fire system. It's actually been commercialized and is being used by the fire service right now. So we went to Indian Cave State Park in Nebraska. This is one of our final demos on the research side. And deployed with some folks who start prescribed burns like this. They walk with a drip torch and set fires behind them, which is pretty easy on flat level ground like this. But when you get to the terrain we're going to survey here, it's very steep and hilly with lots of trees. So it's a bit more dangerous to walk there and set fire lines that are hard to get away from. It also runs down to the river, so it's kind of a perfect place to burn because there's a natural barrier on one side. So we have a system that has miniaturized what they do on manned aircraft, which is it takes these small ping pong balls that have dry material inside, it injects a wet material, and 45 seconds later you have fire. So there's lots of really cool robot questions there. But this is the end result. That's one sphere created that circle of fire. So we have these aerial systems that can fly and start fires, which is really neat. But you run into interesting questions like how could they communicate things that they may know that people may not? So as you're dropping these fireballs, you may see fire outside the fire line. So you know where the boundaries of the fire are supposed to be. If you see fire outside of that, that's a problem that you'll want somebody to address. How could you communicate that to them in a way that they could address that? You can also see all the smoke. So we created a great fire here. And we'd like to thank our partners who helped us to deploy the system. So NSF, Nebraska Game of Parks, and Indian Cave State Parks. If you're interested in that project, like I said, it's been commercialized by Drone Amplified. It's the Ignis system that's being deployed with the Forest Service right now to some of these wildfires. They actually use it to burn areas to try to contain the wildfire. So that's really neat example of it escaping the lab. We also have an aerial water sampling system. This is an old video of it, but we're taking this system to Costa Rica soon. It overcomes really interesting problems with human interaction, like flying out to the middle of the lake to take a water sample. Novice users find it hard to hover very precisely over the water, so that's done by the Autonomy on board. It also makes sure not to cross-contaminate these areas because it's checking for invasive species, so if you cross-contaminate, then that's really bad. And so It's an example of a really neat problem that we were able to solve in Nimbus. And again, end users who aren't specially trained on robots who want to use them in some in-purpose. So we want to make that easier for them. And so that's going to be kind of the motivation for the autonomy stuff I'm going to talk about in a minute. And then the final thing I'm going to show you is a sensor emplacement system. So this is some work we did for DoD. This is a test flight out at White Sands Missile Range. And this was a really good example of DoD starting with a hard problem and continuously making it harder as we went through the project. And so inside that capsule is our aircraft. It's being towed by a larger aircraft because they wanted to get 30-mile range on the system. But when we carried about 18 pounds worth of things, it was hard for us to fly that far. So we capsulized it and we dropped it under parachute. Our system is folded down inside that capsule to be more aerodynamic. As we're falling, we deploy the arms to make the system fly. Then we'll separate from this parachute when we get to a good altitude, fly away. It looks like we're falling, but we're flying, I promise. We land, dig a hole in the ground, put a sensor in it, and then we can fly away again. So again, lots of really interesting robot problems. How do you get enough weight on bit to auger into the ground? You'll see some examples of obstacles we encountered here, rocks in the soil, which the system, we actually changed the system design after this deployment because we realized that we probably wanted to change those cross braces to be able to eject those rocks. But there's the sensor in place in the soil. So those are some fun, hard problems that Nimbus has been involved in solving. I don't work on the mechanism side, I work on the people using it side, although I like to talk to the smart people who work on the mechanism side because it's a pretty cool part of the project. My specific research portfolio is on adapting autonomy for more effective user control. And I'm going to talk about 3 really brief things there, and then go into my really fundamental work, which is on novice interactions with small unmanned aerial vehicles. So this is the part of my work that's funded by my career award, looking at the distancing and communication with these small drones. So I'll pause here. If anybody has questions about the Nimbus videos, I can answer those quickly, or I'll keep going into the adapting autonomy. Okay. So the motivation for the autonomy stuff that I'm looking at now, this is some preliminary work that I'm just really excited about. So I wanted to chat about here, mostly to just hear questions from people and talk to you all about it. It's been something I've chatted about with most of my meetings today because it's something I'm just really excited about. So the idea is, what if a user could pick up a UAS and fly like an expert immediately? So what we found, even within Nimbus, is that our expert pilots have some level of proficiency with which they can accomplish their tasks, but they're not probably experts in the traditional sense of expertise in a system. And they don't have 10,000 hours of training or those sorts of things. And so how can we make people who have something else as their primary job better at flying these systems? So if your normal job is being an eco-hydrologist and you want to use a system to sample water, you maybe want to control it and have it sample in a very specific place, but you don't want to have to do all that control yourself. How can we make that easier for you? There are really interesting things you can do with this, like leverage their understanding to train when they have time to train. So if they're going to go on a field deployment, but they have a couple of days set aside ahead of time to get used to the drone again, you can help them train. You can also exploit quick tests to adapt the controller based on their state. So we're going to talk about that on the next slide. And then you can also create a system that can be fielded consistently. So if they haven't trained recently, you can adapt to that. If they're fatigued or stressed, so you can think of firefighters who have been deploying the Ignis system to wildfires for 6 months now. They're exhausted. Maybe they just have lived in the world that we've lived in for the last 6 months and they're tired or stressed. And so how can you adapt to that and make them more successful on any given day? Hopefully these figures show up really well. I'm just realizing that the yellow may not show up well for some people. But when I say, what if a user could pick up a UAS and fly like an expert immediately? Here's some preliminary work we have on that. So what we did is we had experts, or at least proficient users from our lab. And then we had people from that had very little experience flying drones come in and try to fly some different flight paths. And so one of them was a figure 8. We had them stand kind of on the edge of the cage, fly this figure 8. We demoed it. That's the first picture on the bottom left. That's the autonomous flight path that you would take. And then we had raters go through and qualitatively tell us, does this look like a figure eight or does it not look like a figure eight? It turned out to be really hard to develop any metrics that we could quantitatively say yes figure eight, no figure eight, because you can see even the best one, which is the middle picture, looks mostly like a figure eight, but there's some weirdness at the start and end of it. It doesn't kind of close the loop. So this was the best one we saw. Then on the bottom right is kind of the worst one we saw. The one that raters said this is the furthest from a figure eight. Looks more like a quarter note from music theory. Or a half note, I guess. It's been a while. But if you look above each of those flight paths, you can see the RC control inputs that the user gave. And so if you look at the one that turned out to be a pretty good figure eight, you can see a high frequency and low magnitude input when compared to the one beside it. So the middle one is the person who's doing well, and you can see lots of little changes to kind of hone in on where they're trying to go. On the right, particularly when you look at roll, you can see these like large crests and waves, and you can see that crests and troughs, where you can see that they're trying to do something and then they're going too far and they're overcorrecting and coming back. And so they do eventually kind of get to where they want to be somewhat, but it's really jagged looking. And so one of the things you can think kind of off the top of your head is you would want to smooth those and not have them be such high magnitude, low frequency inputs. So when we think about interrogating user proficiency and improving training, one of the things we want to do is to understand this user proficiency through short interactions and then develop scaffolded learning to improve the expertise, then adapt to meet them on a user skills on a given day. So one of the things that we're doing here is actually developing a multi-part expertise assessment considering many facets of the mental model of the system. So we're looking at auditory inputs they may get. We're looking at, if you give them control inputs, can they tell you what they believe the system would have done as an output? Can you give them vehicle behaviors and then ask how they would get those from control inputs? And then finally, can you ask them to actually do it? So the first three are saying, like, what do you believe would happen, to see if they actually understand kind of book learning of how a system would work. And the final one is actually, can you put that into practice and do it? So there are a lot of people who understand in theory how it would work, but don't know how to give the right inputs to get that behavior. And so that's where the training can come in and try to help them with that. Another part of this problem, which has been published, and so I have citations at the bottom for those who are interested in any of these things that I'll talk about, is user responses to autonomy failures. So this is actually what set us on the user proficiency path. We were curious about replicating some of the findings they've had in autonomous driving with aerial vehicles. So if you give people failures over different time horizons, can they effectively report them and fix them? And does it matter if they're starting out in autonomous mode? Does it take them longer to report them versus if they were in manual mode, if they were controlling the system when it starts doing something wrong? And then if the system's going to fix it or if the user's going to fix it, does that have a big impact? And so we're looking at how they fail in different ways. And so we looked at an altitude failure, which is a dip here, a short diagonal where it deviates either to the left or the right, either close by or far away. So it's either doing a major deviation or a smaller deviation. And so that's dip is altitude failure. Short diagonal is kind of a close failure, it's more subtle. And then long diagonal is a pretty obvious failure, but deviating either to the right or left. And what we found is this was over a 1 second, a 4 second, or a 7 second time horizon. And users did have a slight increase in reporting as the failures got over a longer time horizon, but they also didn't scale directly with how long they had to report it. So that was interesting on the timing and accuracy. We also found that people took longer to report it if they had to fix it themselves. They kind of gave it more time to figure itself out if they were going to have to do something at the end. And so that's some really interesting work, but I'm just not going to talk much about it today because I had promised to talk about something else. So we'll keep going. The final thing I'll tell you about the kind of adapting to users and giving users more effective control is on the fire side. So again, I didn't get to do a ton of work on this before it got commercialized and then it was out of my hands. But when we're looking at specially trained users in complex domains, there are certain things that they can do better than the normal population, and some things that they do worse. So we don't expect them to have a ton of inputs that they want to give to the system, but they do want to infer their expertise, put their expertise into the system in some ways. So one of the ways we looked at doing this was actually in real-time updating to an interface to allow more intelligent sphere deployment at prescribed burns. So on the bottom right, you can see the visual view of a prescribed burn. Then you can see a thermal view above that, and then above that is the actual interface where a user can take those different views and drag the fire line to show how the fire is moving, so that the vehicle can plan a better path to stay outside of where the fire is, because that's where heat is, but B, so that it can actually light the parts that are not burning well so far, and the parts that you don't expect to kind of come together. What you expect for these fire lines to do is eventually they'll merge in together and the whole field will be burned. So you can see where part of the line is dragging. You probably want to help speed that along a little bit. So that is the end of the adapting autonomy section today. Does anybody have questions on that? I'm going to take a sip and then we'll continue with the distancing and communication. All right. So now we'll talk about just general people interacting with small unmanned aerial vehicles. And so I have some more recent work on this that I'm really, really excited about, but I'm not going to tell you about today because it's under submission. So out of respect for that, I'll have that soon. And if you're really interested in this stuff and want to geek out about it, contact me and we can chat more offline on that. Or keep an eye on my Google Scholar page and hopefully you'll see some more publications soon on this. So to give you an overview of what I mean when I say distancing and communication, because it's sometimes hard to tell what people mean when they say that. I mean actual physical distancing from the robot. So how should an aerial vehicle approach you if you were to see one in public and it needed something or is going to do something with you? So you can think about tour guide robots, you can think about delivery robots. How should they approach people? And if they need to communicate something to them, how can they do that? So here's an example of when people interacted with each other in the world and could go into things. So this is actually a nursing home facility was the prompt for this. And so you can see how a family is being led to a loved one's room. In part A, over here on the, here it is, on the figure, they're being led to a loved one's room and something goes wrong with the drone and it needs to land. So it spirals down to show them that it's going to land. Okay, then in part B, there's a tour guide drone and it's taking them from the foyer, which is a large space, down a hallway. And so what we would believe from human-human distancing is as you move from a very large space with a very high ceiling, you're going to stand closer to people. If you go into a smaller space with a lower ceiling, you're going to naturally spread out from people and have a larger personal space zone. So you can see the robot kind of respecting that and going further from people as they go down the hallway to dynamically adjust the spacing. And then the final part C is where we bring these two pieces together. And it's a robot that needs to communicate, hey, you need to clear a path because the medics are trying to get this person out. But it's also maintaining kind of less space from people because it's a larger area. So in order to convey that message, it's getting closer to them. So part C, we will not talk about yet because I don't know enough about parts A and B to tell you anything super interesting on that front, but it's where we're headed with this work. So I'm going to talk to you a little bit about motivation. Hopefully I've motivated it enough, but we're going to talk about motivation for this kind of more fundamental work, then some applications of it. We'll talk about the distancing work and then the communication, ending up with some future work. And all of this with the goal to convince you that distancing and communicative flight paths are important fundamentals in human SUAS interactions. So I've alluded to this a couple of times, but Amazon has promised us all they're going to deliver packages to our house, which is wonderful and somewhat terrifying. We don't know how that interaction is going to take place because we don't know. I mean, my dog does not particularly enjoy interacting with drones, and my baby really does. He really thinks it's fun to chase them. So those are both problems in their own right. One is a dog who wants to attack it, and the other one is a baby who wants to lovingly attack it, but probably should not get chopped up for having such a vision. The other thing that's interesting is lots of people are taking their own drone systems, whether they look safe or not. I'm highly skeptical of the one on the bottom here, but it's a camera drone that people used. This was at a running of the bulls in Virginia. And the interesting thing about that day, the reason that this picture is actually important in this talk, is that that drone injured 5 people and the bulls only injured 2. So we have a right to be skeptical of this system. Now, drones have come a long way since this one was deployed, but I'm always, as most human robot interaction researchers are, deeply skeptical of what humans will put out into the world to interact with other people or near other people. So that's kind of the external motivation. A more internal, a closer piece of motivation is when I was in graduate school, pardon the quality of this, it's not your computer, it's that this was recorded on videotape and then digitized a long, long time ago. And this is small helicopters, like fist-sized helicopters, being used in a Midsummer Night's Dream play at Texas A&M when I was there. And we had middle schoolers fly them, and they were really good at it, as you can tell. So this is the same crash from a different perspective. So you can see this fairy comes down from what she's doing, and she relaunches the drone, which immediately crashes again, this time into the audience. There's no autonomy on these systems. Like I said, they're hand flown by middle schoolers because we were very bright when we thought about this as a great STEM outreach activity. But the interesting thing about this, there's 2 interesting things that I'll tell you. One is the idea of social proof. People don't know what to do. And when they don't know what to do, they look around and see what other people are doing, and they do that. So if these systems crashed on stage and the fairy had like gently relaunched them into the air, then with about 90% probability, people in the audience would do the same thing. They'd pick it up, they'd hold it in their hands, and they'd wait for it to take back off. That was wonderful. But if they had not crashed on stage when they crashed in the audience the first time, what people would do is they would look at this helicopter and they would think it came from the air and it belongs in the air. And they would toss it, or they would throw it, or in some way try to return it to the air. But those of you who know how helicopters fly know that that's not a great idea. And it would generally come down and hit them or someone else in the audience. So we not only had middle schoolers crashing these into people, we also had people chucking them at each other in the audience or at the fairies or whatever. So the fairies became very proactive at like stomping out to the audience and demanding the helicopter back so that it wouldn't hit other audience members. They became quite protective of their baby drones, and they really liked them. The other side of that coin on people not interacting appropriately is that the fairies became very accustomed to these small helicopters flying above their heads. They became very comfortable with them. We let them stick their fingers in the rotors and see that it wasn't going to hurt anybody. I mean, if it got in your hair, that was not great. Luckily, we only had an incident where it went into a wig and the student didn't turn it off and it like wound its way deep into the wig. So that was not promising, but the rest of them, they were really easygoing. They didn't hurt anybody. It was totally fine. We also had a military grade, fully carbon fiber system that would fly in only at the beginning and the end. And the fairies would kind of dance it in. And when we had that one come in, after having gotten them really comfortable with these small ones, they would interact really, like they'd play with it, they'd tap on it, and they didn't understand the differences in the size and the safety of these systems. And so we had to tell them, no, that one's the flying weed whacker of death. Don't touch it, don't look at it, don't stand near it. It's just gonna come in and do its thing and then go away. These are fun little baby fairies. And so kind of trying to understand people's perception of safety in public was also interesting when we were having these early interactions. This is just one of my very favorite pictures because she looks like, please don't crash. And that's how we all feel when we're flying drones. So she's about to catch that drone out of the air. Okay, so now we'll go back to the fundamental topics of distancing and communication. Now that you know that Amazon wants to deliver things to your house and that's troubling in certain ways, there's yahoos flying drones and you should be deeply skeptical of them. And people react in crazy ways that you can never predict, as we all know, as human-robot interaction researchers. So when we started investigating distancing with these systems, the first thing we thought was, hey, let's replicate some human-human studies and understand how people perceive the drone approaches. So we want to know both how people will prefer to be approached, but also what we can expect as they approach these vehicles. And so what people found in early studies with humans and with robots is if you have a person approach something or someone, they will stop about the same place that they would want someone else to stop when approaching them. So that's really nice, this idea of the bidirectional distancing. Whether you're the approacher or the approachee, you end up with roughly the same space, which was not always thought to be true, because there was thought to be something about whether you're in control or not would have an impact, but doesn't seem to. So one of the first things I did when I arrived here at University of Nebraska is get a study room and recreate the study space that was well known in human interactions. And so it's the size and ceiling height and everything of an accepted test bed. And so I can kind of compare to their numbers better. And so I got this really cool collapsible wall that sections off my interaction space. So it's got a Vicon space, so that I can precisely control the vehicles, and that's nice as well. One thing I did do is reverse which corner the robot and the subject are in. So the subject stays close to the door, and that's just so that they're close to the exit. If something were to go wrong, you can kind of ditch back over the wall and not be stuck in this room with a robot. And so that's where we started. So when I say distancing, I mean actually like literally the robot will just approach the person. And when the person feels uncomfortable, they'll say stop. And so we had a ground robot, a telepresence robot, it's the double telepresence robot, approach a person while it's at its maximum height of 5 feet. And then we had an aerial robot take off, climb to 5 feet, and then approach the person. And we had them approach rather slowly at 0.2 meters per second. So they approach, person says stop, and the robot stops. So that's great. Then we had the aerial robot, it takes off, approaches the person says stop, and that's also great. It's relatively slow, like I said, 0.2 meters per second is not very fast, but that was recommended from human-human interaction studies to make sure that you don't kind of overshoot as you're approaching them. It's slow enough that they feel like they can react and say stop, and they believe you'll stop. And it also gives them more time to kind of process how things are going. It's also, when we're dealing with robots, for safety purposes, so that, that it's not going really fast or flying really aggressively. And if it does the wrong thing, then we can't take control. So what we found was that there was increased distance and negative affect with the aerial vehicle compared to the telepresence robot, which reviewers found completely unsurprising, because telepresence robots are supposed to interact closely with people and drones really aren't. But what was troubling to me is the fact that people generally stop the aerial vehicle about 2 feet away. So if you stick your arm out in front of you, that's about 2 feet, where you can just really put your fingers right in the blades of the aircraft. This one did not have any sort of a prop guard or anything, so it was just open blades coming towards you. One thing that's also interesting is we tested this, we thought maybe it's the 5 feet. I thought eye height would be the scariest height. But we tested it with 3 feet, so kind of belly height, which as mammals, we should protect our belly. That's where important things live. The things that live outside your head that are important live kind of towards your belly. And then also at 7 feet. And it turned out people didn't really care. They stopped them all about 2 feet away. So we have some other stuff going on that we're interested in testing, but that's as much as we've published so far on the distancing work. So now we're gonna pivot over to the gesture work. So again, I'll motivate it. Hopefully you're with me by now, but if you're not, I'll give you one more chance to get with me on the motivation. They're becoming used in more, drones are becoming used in more public facing applications, and they need to be able to communicate with people who may not be operating them. So if a drone needs your help or wants to lead you somewhere, then you want to be able to understand that maybe, or some people will. One example for this is the prescribed fire domain. If we're dropping fireballs, we want to be able to communicate with you maybe that we're going to drop fireballs. That could be relevant to you. Another thing we may want to communicate is if the fire is about to jump outside the line, you would want to know that. If there are embers blowing that are likely to start another fire, that's something else that would be kind of domain specific to tell you. But another thing that would be kind of general in the world is if it's going to land, you probably want to know that so that you can make sure you're outside the space. So that would be important for package delivery, photography, or other applications. So when we think about challenges with communicative flight paths, there's kind of two sets of challenges that I'm going to talk about today. The first one is content, or what can be communicated and how it can be communicated. So for this, I've looked at different state label candidates. So what can you try to communicate? Flight path creation. So how can you try to communicate that? having people assign labels, and then trying to generalize that. So it's an iterative circle. I've gone around it a couple of times. I still don't have a ton of answers, and today's talk will be a little bit unsatisfying in that I have more answers than I'm able to give you, but again, I'll tell you really, really soon. So keep an eye out for that if you're interested. But we're going to focus more on this content question than we are the perception question. I'm going to play a video here for the perception question, and that'll be as much as I talk about that. But again, hopefully that'll be out soon. I just don't have any slides that I'm able to present yet on it. The perception question is really interesting because it's one of the reasons that flight paths are attractive. So one reason that you want to be able to fly a flight path is more people and people further away can receive your communication than if you were trying to do lights or sounds on board the aircraft. And so you can send messages further potentially if people can receive them, but you need them to be able to understand them, and you need to understand how occlusion could impact that. So in a rainforest, there's likely to be a lot of occlusion. This one's just talking about self-occlusion. So in this case, what we're looking at, oh no, my video break, there it is. Okay, hopefully you can see this figure 8. It's a vertical figure 8 this time. I really like figure 8s, I'm sorry. And so it's a drone that flies a figure 8 configuration in space. And then you can see to the right, there's these 3 different viewpoints that you're looking at. So in the bottom one, it's fully self-occluding. It's just, you can only see the vertical motion. In the middle one, you can start to see some of the motion. And in the top one, you can see basically a straight on view of the figure 8. And so one of the questions we had was, how do people perceive this from these different angles? And can they accurately predict which flight path it is? If they know there's only a set of 6 flight paths, can they pick which one is being communicated to them with any reasonable level of accuracy? And so what we found is yes. For the most part, across a large set of flight paths, they could pick with 90% accuracy once you got to about 20 degrees offset. So some of them they could pick actually pretty precisely at 0 degrees because there were interesting things about the gesture that changed how they perceived it. But again, I won't talk very much about that today. I just thought this was a cool video that I wanted to show you all because I just got it. So we'll talk about the content and what can be communicated. So this is primarily work from 2 different papers that I'm happy to have you look up or to chat with you more about. The first one is looking at state label candidates. So we identified a set of 7 labels that we wanted to assign to things. And then we went and found some avian gestures and tried to see if people just naturally understood any of these interspecies communication by naturally applying some of these gestures to it. So one example of that we'll talk about on the next page is the idea that a lost signal or a lost sensor might be a figure 8. So if you've ever had your magnetometer become uncalibrated on your iPhone, you can do this figure 8 with it and it'll recalibrate your magnetometer. And so I just kind of thought that was a template people had and they might apply it. Turns out no, but that's okay. Again, I really like figure 8s. And so from there, once we had figured out kind of how people apply these different labels, we had people create their own labels, and we'll talk more about that as well. So the first one's looking at avian flight paths. So we had 2 small MTurk studies where we tried to see if users could apply a consistent label when choosing between either 2 or 7 options. So in one case, they got 2 of these 7 labels, and in the other one, they could pick any of the 7 that they wanted to. So there's lost signal, change position, landing, miss goal, draw attention, lost sensor, and low battery. And what we really found was that they could use some of these and apply them pretty easily. People pretty consistently applied spiral to indicate landing, which was nice because it not only tells you that is landing, but also where it's landing, right? It gets in this kind of concentric circle and shows you where it's going to be. Circle could be used to attract attention. It had a pretty high agreement, and we thought those states could probably be used. So here's an example of the videos that we showed for those. And the lead-in is very dramatic. So we had 64 participants label these videos. And so circle was labeled as draw attention. And we got lots of comments about our sweet white background that we had put up there that we thought would be big enough, but was not. So some people did actually pick lost sensor for figure 8, but it was a lot fewer than I thought would pick it. They also chose it for change position. Left, right, we actually thought would be kind of like shaking your head no, but people didn't seem to perceive that, at least in this study, as a shaking no. Loop was labeled as landing. Almost anything that came close to the ground, people perceived as landing because there was a large altitude change, which will be a consistent story that we get from users. Spiral was also labeled as landing. And this one takes a little bit longer. People also seem to infer things about the tape on the floor, which were not meant to be anything other than markers for other studies. So this is swoop. And then we had undulate was draw attention, which is a very attention grabbing gesture and kind of fun. So then we had up down, which was also low agreement from participants. And I thought it would be kind of like nodding. It would be like a yes or an agreement of some kind. So that was that one. There we go. Then from there, we went and we wanted people to create their own flight paths. And so we had 20 participants that were half male, half female, in a wide range of participant ages, so from 19 to 79. And we had them try to design gestures that a drone could communicate, a set for bystanders and a set to the operator. So landing, low battery, signal lost, and attract attention to bystanders. And then for the operator, attract attention, lost sensor, area of interest, and miss goal. And I don't tell you this later, but it turns out that the communicating to operator, the naive users didn't really have a sense for those states. And so they said they had a really hard time designing those. So like I said, we don't come back to that. But the way we had them do this is demonstrated in the HRI video. It's actually a pretty good video that I like, but I'm not going to show it here today. So only one, we had participants sit down and we gave them a piece of paper with those 7 states on it. We had them draw out what they thought it would do. And then we gave them a palm-sized model, which someone has stolen from my office, or usually I show it in this talk. And so we gave them just a little one and we had them kind of show us, we said, you have from the table to your shoulders and then kind of the width of your shoulders. And so show us in this box what you think it would do. And then we would go into the Vicon cage and we have a nice kind of waypoint recorder where we would walk it through what it was going to do and have it replay it for people. And then we'd have people tell us, did you think that's what you wanted to do? Is that what you planned for the drone to do? And most people said yes. So when they were designing them, only one person needed more time. Only 4 were identified as incorrect. So when we replayed them, people said, no, that's not really what I meant. But all of those we were able to correct to what they thought. And so when we reported them, we actually talked about what they wanted it to be, not what it was. And so one of the ones that was pretty common was physically impossible. So it was a waggle. They wanted it to stay still and do this, like it's an airplane waggling its wings. But we couldn't do that. But what we could do is something like this, where it's kind of rocking in place. And they said that was close enough and they were fine with it. So from this, we designed a taxonomy to kind of label these different flight paths that were created. And I'll only talk about a couple interesting things, the bullet points about the taxonomy, but I go into a lot more detail in the paper. So complexity and space were adopted from other elicitation studies. So where they had people kind of tell you what they would do with this technology. And then cyclicity was only used in other SUAS work. So how cyclic or random was the flight path. Command is a more specific version of dimension, which is also used in the elicitation studies. And the most interesting thing to me was that altitude was mentioned explicitly by every participant for every flight path. So they do perceive that to be a very important component of the flight path, whether it's stable, variable, or decreasing. So that sounds really exciting. And then I get to the commonly suggested flight paths and people are like, womp womp, because they're not super interesting, right? People agreed on them because they're basically what you're trying to describe, right? Landing, I would start where I am and I would go down to the ground and land. So that was for landing or attract attention. For area of interest, miss goal or target or attract attention, people thought kind of a big circle. For low battery or attract attention, people thought a bouncing flight path and maybe either going like really big or even getting smaller as it went along. And so that's interesting because it's kind of a misunderstanding of low battery, right? If you have a low battery, then doing this motion is going to be really, really bad. And then sensor lost or signal lost, they wanted to yaw in a circle. And so that was interesting because it was one of the very few times that people actually used yaw. So when we think about the common subcategories for the state labels, we can start to understand across people, what do they think? And so the bolded categories here are the ones that kind of stood out from that category. So all of the flight paths use space indirectly. They kind of meandered, except for landing. For landing, they just want to go straight down. All of them were very simple paths, so they were basically just one line rather than being multiple pieces, except for low battery and signal lost. And so you can start to kind of, or we started to kind of generate new flight paths from what we learned here. And so you can see some examples that kind of meet these criteria are for low battery, you start out high and then you come down, and then as you get closer, you kind of bounce before you land. And so that shows people that you are coming into land, but kind of gathers some attention as you're about to do so. If you miss a goal, they had it kind of choreograph and say like, oh, I'm turning around and coming back. So when I reflect on the elicitation study method, it was really neat to conduct this kind of formative research with novice users. It can allow insights into the underlying assumption, like we just talked about. So area of interest and missed goal were likely curvilinear. They were curvy paths because they involve circling around a space, right? Honing in on what you're trying to do. But participants did express some difficulty in creating gestures. Partially, we think it's due to a lack of understanding of the technology. Like I said, most of them didn't use yaw at all, or even talk about yaw in any way. So all of them talked about altitude. Almost none of them talked about yaw. And so that's partially probably because they haven't operated one of these vehicles. They don't necessarily know what it can do. Also, this showed up in the increasing altitude for low battery. Another part of creating the gestures could be that context is important. So one of the things I've talked about with some people is the idea of like a Mad Libs, where you have like a vignette where you tell them kind of, this is the setting. Now I need you to give something for this middle part, and then it's going to do this other thing. And you can show them on either side what it's going to do and ask them to give you this kind of middle piece to connect the two. So that's one thing that we're thinking about. That we had this assumption that experience with other technologies would translate to this, and that didn't seem to be true. So we're hoping to run reverse elicitation studies, so have them apply labels to the paths that were generated by other people and compare this with the Avian path work that I talked about earlier. We also want to understand what states would be important. So what states would you need to respond to, and how would you respond to different states? And so asking people, what do you think a drone would need to communicate to you, and how would you respond to that communication? So if it's going to land, does it need you to clear the area? So does this tie some of the earlier states together? And then we're considering the addition of lights and sound and how that might work and what that would indicate to people. So distancing, we're going to extend this to other platforms, so different sizes, outdoor environments, and different altitudes. I talked a little bit about that. For gestures, we're adding new states, investigating the impact of a visible goal state, or this idea of vignettes, and testing those in outdoor environments, and then eventually merging those two with different, very varied vehicles in realistic environments. Hopefully you care, because these vehicles are becoming more prevalent in public spaces, and we all want to be invested in interacting safely, maintaining some sense of space through comfortable approaches, and understanding concerning states through communicative flight paths. Quick plug for Nimbus Lab and Facilities. I think this picture of the drones is hilarious because we have these teeny tiny ones, and then we have this big one that I can barely pick up. We also have an indoor flying arena. We have an outdoor space that hasn't made it to the slide yet, and we can fabricate things. Here's my thank you to NSF for all the monies, and a picture of the fun students I get to work with. So does anybody have questions?
Feel free to either raise your hand or jump right in for the first one. If not, Aaron gets to be the professor to call on somebody. Well, I have, well, Ruben has raised his hand. So.
Oh, very good.
You're up, Ruben.
Hi, really interesting work. I was curious about, so you mentioned the gestures of sort of going up and down and left to right as sort of, you were expecting them to mirror sort of social gestures as head motion. And what sort of struck me there was some of the work on how people sometimes need priming to interpret a robot's motion as social. So I'm wondering, like, how dependent do you think sort of gesture interpretation is on either priming from like what, model people are using for the robot's behavior, or are they thinking of it as a character or something controlled, but something like that?
So that's a great question. That's super interesting. And that's where, you know, combining, so I do some work with Dan Zafer, who's done really cool stuff with drones as well, and made work to make them more communicative and social, right? And so one of the things he did was explicitly adding lights that look like eyeballs, right? And so if it had these lights that look like eyeballs, then would you see it as shaking its head no? Would you see it as nodding yes? I think that's a great question, and one that's we haven't explored yet, but I do think that's good. And that is one of the, I guess, reasons why we think these vignettes would be more powerful in having people create things, right? They have some sense of what it was doing and what it's going to do. And the only reason we've been hesitant is because we're a little bit worried that what if we prime the wrong thing and then they give us an answer that then nobody later understands. So I think it's a really interesting problem, and I appreciate the feedback or the input.
Actually, I do have a question. Do you think it would be useful to combine different types of like movement and sound, for example? So, for example, if someone couldn't see, or if someone was deaf, communicating through that, do you think that would be useful?
Yeah, so I always think that more accessibility is better, right? So obviously these are not super accessible right now, and they are leaving some people out. But I think one of the things that I've been hesitant about adding sound is actually the sound it creates is in some ways its own communication, right? So I guess I had the sound muted for all these videos because it's disruptive to my talk for you to hear them. But what you would normally hear in this like as it's going back and forth. And so I do think those kind of create their own sense of how people interpret them. And so I think that does make people in some ways interpret them more aggressively possibly than they are intended to be. And that may be why people, so one of the things we found, I guess this isn't an answer to your question, but one of the things that I find interesting that we found is that people who have negative attitudes towards robots generally tend towards these like negative state, applying negative states to them. So things like do not enter, stay away from this area. Like they think it's like a guard being mean, not a helpful, happy robot. And part of this is potentially the priming, right? It looks like something that, you know, somebody may use in a military or a police context. It doesn't look like a happy, fun tour guide robot. And so most people are reacting negatively and applying negative labels. And so partially that could be overcome, to get back to your question, by including sound that says like, hey, friend, follow me. But that does, again, we're trying to figure out how would you interpret this if you saw it flying and taking pictures without totally changing that kind of interaction modality and adding more things that people may not have. So how could people leverage the inherent communications that are already there? And one of those is the sound that's generated by the robot, but it may not be in the same way that you would design the sound. So one question that's kind of open for me is how can you design flight paths that generate sound that may be more approachable, right? Or that how can you leverage the way the vehicle already interacts to make it better interact?
Jessica?
One last thing I think would be really interesting to look into would be to see whether a more curved and less sharp robot drone shape, I guess, if it would give people a better perception of the robot, because, you know, if you have a robot that's just the bare minimum, typically it'll be very linear, which people can interpret as being aggressive, I would assume.
Yeah. We do use very utilitarian robots because we're loading them down with as much as humanly possible to do the cool stuff we're doing. So they're not the sexiest robots, that's for sure.
You cut the fairing off to get the sensor on it. Teska, I see your hand is up.
Yeah, thanks for the great talk. This is really interesting. I did have a question about how other indicators might be used in addition to navigation, but you've already touched on that question a little bit. So my other question is, how do you think that distance affects how people perceive this motion? Because I imagine, especially for these outdoor settings, a big plus of using these gestures rather than sounds or blinking lights is that you can see it at more of a distance. But I imagine that also affects how people perceive what the robot's trying to communicate.
So that's a great question, and that's one that's open for us. So part of the perception question we're actually looking at is the next part is how big does it have to be, right? Like, is there foveal size or something that is actually quite important. Another part of that I didn't touch on even a little bit today is the idea of background noise. So one of the cool things we get to look at is insects are actually really great at projecting different gestures over long distances in the presence of background noise. So how do they do that? How do they kind of observe the background and then amplify their signal such that it's received far away? So that is one of the cool things we're looking at, and it's one of the things that our DoD sponsor is also relatively interested in, is how you can either amplify reception of signals or suppress those.
Mm-hmm. I'm also wondering because in the study that you're showing, some of those gestures might be really exaggerated in the form of like when you're that close to the robot, a nodding motion that takes the drone way up to the ceiling and down is a little bit overkill. But if you're looking at, you know, a robot outdoors at a distance, something like that is actually it's a very clear and obvious indicator of it trying to communicate. And so I imagine that that'll affect like how natural that communication seems, where those sort of large motions might be easier to control with the drone, but have more intentionality ascribed to it when you're looking at it from a distance rather than up close.
Right. Yeah. No, that definitely makes sense. And one of the things I also didn't talk about was the rainforest work. One of the things we're looking at too is that'll be over larger distances, but also potentially with more distributed users. So in the prescribed fire scenario and in that one, the robot is likely to be kind of in the center of a number of users that'll be on the outside. And so that's why we thought perspective was the first one to look at, is like, how do you rotate around it, but also distance will become one of the things to look at as we move forward. Thank you.
Thanks.
Other questions before I ask mine? Okay, so mine is kind of similar to some of these comments in that one of the big issues with drones is wind, and you know, wind will come along and the drone will fight the wind to do station keeping or maintain its desired path. But then there's this thing of as the bystanders or even the users don't really know that this is happening, right? They'll just see like the drone pitch and turn and kind of make an aggressive motion because of a gust or something like that. And I'm curious to know if there are lessons to be learned in terms of how to both deal with wind, but at the same time not come across as being particularly dangerous, right? If you see a drone try to fight a wind in some types of wind, it's pretty scary to watch.
Yeah. So I think that's a great question. I think one of the ways is obviously depending on what you're trying to communicate. There would be a way almost to kind of, if you think about dancers, right, in the world, one of the things they do well is if they mess up or they're about to fall, they do so gracefully such that like at least computer scientists aren't going to notice that that's what they were doing. We're a little bit that way in the world, right? So we'll just believe it. They'll go along with it. They look graceful. We generally look less graceful. So we're impressed by that. And so one of the ways is, yeah, like, can you turn it into a larger movement that would then be kind of understood as reassuring or just kind of a normal thing, right? So can you play it off in some ways? But yes, you're right. The fighting the wind is a tough one that people who are untrained interpret it as being jittery or about to fail in some ways. And so that's where I do think kind of if you are willing to give a little bit and then circle back, it'll show that you're kind of doing something there. You're doing some sort of station keeping, but it makes you just look more kind of hanging out. And right, so I think that could be good.
Sacrifice some performance to keep people calm.
Yeah.
I do like the idea of kind of failing gracefully and make it, I meant to do that. You know?
Oh, exactly.
Okay, unless there's any other questions, we are at time. Oh, sorry, my camera just went out of focus. Unless there are other questions, we are at time. We'll stick around just a little bit longer, but I do want to release everybody into the wild, especially the warm wild here in Pittsburgh today. And I don't want to make Brian and Stephanie stay on unnecessarily. So if everybody, let's just thank Brittany for her talk today. So yay. I don't know if any of you know where the clap feature is on your thing here. And again, if you continue to have questions, we'll leave this session running just a bit longer, but I do want to give Brian and the others a chance to close out their week. This talk has been recorded. It will be posted on YouTube. So if there's something you saw that you want to go back and check, it's available there.